Hey, this is Leach with Simpson Math, and today we're looking at sampling distributions and specifically the central limit theorem. In the last video, we looked at at an applet to make sure that we understood the central limit theorem, how the standard deviation of the sampling distribution works. That's the table that you see here, and then also the means. So if you haven't seen that video, go check that video out, and then come back and pick up here so we can do some examples. All right, let's summarize what we talked about last time. So if I have a random variable x and I take a sample of a whole bunch of x's and find their mean and look at the sampling distribution of those means, we're going to call that mean x bar. So x bar can be modeled as a normal distribution. That's what the capital N means, a normal distribution with a mean of the population mean. So whatever the population mean is the mean of the normal model of my sample means. Lots of means. And then for the standard deviation, if I take the population standard deviation and then divide it by the square root of n, that is the standard deviation of the sampling distribution of x bars. So all in those applets, all those blue graphs that were at the end, they all had a mean that was the same as a population, and they all had a standard deviation that is the population standard deviation divided by the square root of n. And then that is true. These two numbers are true regardless. The last component is the shape, and that's this. So it is, we get that it's normal when one of these two things is true. When one, the distribution of x, which is the population distribution, is normally distributed. I need to correct that. X is normal is normally. That should read x is normally distributed. Wow. So if x is normally distributed, then the sampling distribution is also going to be normally distributed. And then secondly, if we don't know the shape, or if we know that it is not normal, then the sample size has to be at least 30. And so that's n has to be greater than or equal to 30. And if that's the case, then it's safe to approximate normality using the central limit theorem. So if my population is normal, I do not care about the sample size, then the sampling distribution will then be normal. But if we don't know if it's normal, or we know for a fact it's not normal, then the sample size has to be big. And in this course, we're going to say big is bigger than 30. When that's the case, then it's also going to be, the sampling distribution is going to be normal. All right, so let's take a look at these examples. So you're wanting to get out of Temple, Texas desperately. So you take off like a bat out of you-know-where, driving south on I-35 to spend an evening in Austin, Texas. Most people drive close to the speed limit, but some, like you, are speeding a lot. So the distribution of speeds, which is the velocity, is skewed to the right, skewed towards those bigger values, those who speed. This stretch of the highway has a speed limit of 75 miles per hour. Suppose that the speeds of all vehicles along this section of the interstate have a mean speed of 73 miles per hour and a standard deviation of 7 miles per hour. Texas DPS monitors speeds and traffic flow by a variety of methods. Suppose they were to randomly select 49 vehicles and find their speed in miles per hour. So in words, let's describe the random variable x. So the random variable x, that's talking about a value from my population. So this would be the speed of a vehicle on I-35. We'll say on I-35. Really, it's on this stretch of I-35, but I'll just abbreviate it by saying on I-35. All right, in words, let's describe what this capital X bar is. Well, it's this thing, the speed of a vehicle on I-35, but it's mean. And in here, I do need to mention the sample size. So this is the mean, or the average, the mean speed of 49 vehicles on I-35. All right, so let's put this together with what our sampling distribution will be. Now, what about the shape? So we're told that this is skewed. So this is not normal. Where was that skewness? Here it is. So we're told that the distribution of speeds is skewed to the right. So it's not normal. So if my sample size is small, small being less than 30, then problem stops here, we can't do it. It has to be bigger than 30. So I look for my sample size and it's 49. We can do this. So that means that this distribution is normally distributed. So I'll abbreviate that with that capital N. All right. So now this next blank is my mean. My mean is going to be the same thing as the mean of the population. So 73. And then for the standard deviation, it is not just 7. My standard deviation, the standard deviation of x bar is going to equal just the standard deviation of x over the square root of n. Well, what's the standard deviation of x? It's this 7. So it's 7 over the square root of, what's my n? My n is at 49. So 7 over square root of 49. Now, that seems very nice and academically friendly. 7 divided by, what's the square root of 49? 7, which is 1. Now, for your homework, I only need to see this. So I want you to write 7 over square root of 49. I want to see that formula plugged in. You can then clarify for yourself that this is going to be the same thing as normal distribution of that 73, mean of 73, standard deviation of 1. You can clarify that for yourself or in a second line for me, but I want to see not the algebra, but the formula use. So even if it simplifies nicely, give it to me first and then give me the value if you want to. More often than not, it's going to be a decimal approximation. But for this first example, I wanted to have a nice, easy standard deviation. All right, so what's the probability that the sample of 49 vehicles will have an average mean speed that is considered speeding? That's more than 75 miles per hour. So let's make my graph. In this case, I'm making my graph based off of this normal distribution, my normal distribution of x bar. So smack dab in the middle is 73. I have my standard deviation right here, which is 1. So let me add a few tick marks just for myself, at least in this first example. So if I go up 1 standard deviation, that's 74. Go up another standard deviation, 75. Up another one, 76. Then I can go down 1, this would be 72. Down 1, this would be 71. Down another one, this would be 70. All right. So what I'm asking is more than 75 miles per hour. So the probability that x bar, so not x, this is x bar. This distribution is a distribution that is x bar. Actually, let me just put this on the x-axis right here. This is x bar, and these units are miles per hour. So these are average speeds, the average of 49. All right. So the probability that x bar is greater than 75. Now, since this is a continuous distribution, I'm not caring about whether it's greater than or equal to. We're just going to say greater than. So I'm going to draw here at 75 and then shade up and say that this is the space that I'm looking for. All right, now we could approximate this using the 68, 95, 99.7 rule. And I would know that that from 71 to 75 would be 95%. And then I have 5% left over. If I subtract 100 minus 95 is 5%. And so this top bit is gross is 2.5%. So we know it's about 2.5%, but I'm going to open up Desmos so we can find out what it is exactly. All right, so I have Desmos open, and let's review the steps of getting this normal model in here. So I have Desmos open. I'm going to press the functions button, press distributions, then normal distributions, and my mean is 73, comma, my standard deviation. And now, just to show you, I could just type in 1, but I'm going to show you that we can also type in the formula so it's exactly. So I'm going to do 7 and then the division button. And then I need to get my square root, which is way down at the bottom, square root of, and then 49. Notice you could type in the 1, but what if when you did this, you got a decimal approximation? I would actually rather you type in this exact number instead of the decimal approximation. It will in turn make your answers, your approximations, be better. All right, now I'm going to press the plus magnifying glass to zoom in. And then I'm going to check the find cumulative probability button. And if you're like, whoa, he's going too fast, I have a video that I've covered this app already. So I'm going a little bit quicker right here. So if you need a little bit more time with this, go check out that video. It was about two back in the series. All right, and then I can go from my minimum, in this case, is 75, to my maximum. Well, it's infinity, so I'm going to leave it at that infinity. All right, so here we have it. You can see in the picture above that it's from 75 up, and this is actually, instead of just 2.5%, it's actually a little bit more accurate to be 2.28. So 2.28%, or as a decimal, that was at 0.02275. So decimals, percents, whatever. Let me make that percent symbol a little bit nicer looking. There we go. All right, so that answers that question. All right, let's move on. E, what is the probability that the sample of 49 vehicles will have an average mean speed that falls between the interval of 71.5 and 73.5? So again, let's draw my mean at 73, my standard deviation at 1, put a little bit off center, because then 73.5 is halfway between here at 73.5. If I go down one standard deviation, that's 72. Go down another one, that's 71. So 71.5 is between those right here at 71.5. And then let's color this in. All right. And I'm looking for this value. So this is the probability that 71.5 is less than my x bar, which is less than 73.5. And so we see that this is the x bar is between 71.5 and 73.5, right? So I'm going to go over to my calculator. I'll just change my minimum from 71.5 to my maximum, which is 73.5. Notice every time I'm including my picture, my probability statement, and my answer. So here, this is 62.47%, or as a decimal, 0.6247. All right, last question. Let's find the IQR of x bar. So this IQR, that's the middle 50%. So this is one of these middle percent questions. So I'm going to draw my picture again. 73 in the middle, standard deviation of 1. So somewhere about here to about here, and color it in. And then so I'm going to be looking for my IQR, which is the middle 50%, and those endpoints, which is Q3 and Q1. So Q3 minus Q1. So I want to know, I know that this is 50%. I need to know these numbers, and then I'll subtract them. So this is my Q3 and my Q1 I need to find. Let's just go ahead and go over to the calculator. To do this, I need to give the normal distribution a name. I'm going to tap in front because I need to give it a name, so a specific letter. Since we're talking about vehicles, let's do V. V equals. Why not? Pick your favorite letter. I'm going to do V today. All right. Then I'm going to say that V again, V, and then dot, or the decimal, or the period, dot, and then now the functions button, and then inverse CDF. And then here comes the inverse part. So in a minute, I need to type in a percentile. With this being the middle 50%, we can do our middle percent dance. Everything adds up to 100%. Everything under this curve is 100%. If this is the middle 50% and I subtract it out, I'm left with, well, 50%. So that means collectively in both of these wings is 50%. Well, this is a perfectly symmetric distribution, So I can split that in half. So that means that this section is 25%. So is this section 25%. Add those up. 25 plus 50 plus 25. You see we get the 100. What's happening is right here, this is the 25th percentile. And then right here, this is the 75th percentile. So if I'm looking at this line that I labeled 75, it's there and less than is 75. Remember, this inverse norm only works less than. So I'm going to go to my calculator and type in 0.25 in my v.inverse EDF, and it pops back 72.33. So I'm going to label this, my Q1, as 72.33. And then I can, I'm lazy, so I'm just going to change that one to be 0.75, and it's 73.67. So my Q3 is 73.67. So my probability that 72 rather, 0.33 is less than X bar, which is less than 73.67, is my 50%. So there's my that complete statement, that middle percent. So that means that Q3 is 73.67, Q1 is 72.33, and my IQR is 73.67 minus 72.33. And we subtract this, we're going to then get 1 point. With the way that it's rounding, it's 3.4. We end up with the IQR being 1.34 miles per hour. Those units would be helpful on each of these. All right, so there you have it. This is how we use these sampling distributions. So notice, once we get this distribution right here, the only new part about this compared to the normal model business is just this part. This is the only new part. Once we get that, all these normal model questions are pretty much the same thing. In our next lecture, we're going to then just be doing more of the same practice, but I'm going to make it a little bit bigger deal about making sure that we're aware of whether we're dealing with the sampling distribution or whether we're dealing with just our population. And then secondly, also looking at whether we can start making some decisions about things using this the sampling distribution. All right, so I'll see you next time.